Today, we're going to learn how to deal with combined loading modes during fatigue. Now, thus far in our investigation of fatigue, we focused on a single type of loading, say axial loading or bending or transverse shear stress. However, in real structures, most often they are subject to combined types of loading, where you can have both axial loading, two-plane bending, as well as torsional shear stress, where these can be acting statically or dynamically in combination with each other. So some of these loads can be dynamic, resulting in fatigue, and others can be static loads, loads that are carried continuously. So the question becomes, how do we apply them together to assess fatigue resistance? Well, back when we learned about static failure theories, we learned about distortion energy, the von Mises stress criterion, where we could take all of the different types of stress, the normal stresses and the shear stresses, and combine them into a singular stress against which we can check for yielding or check for failure, meaning rupture. Now let's consider the common case of a shaft that's subject to collinear axial loads. So all the loads are, say, carried in the x direction from axial and bending stresses in the same direction, along with torsional shear stresses, so a shear stress carried in that structure. In that case, our equations simplify. Our shear stress equation simplifies to the following. The von Mises stress simplifies to the following, where it's the square root of the normal stress squared plus 3 times our shear stress squared. Now, let's consider von Mises stress not only as a static value, but as a fatigue stress, meaning we can find a stress amplitude in terms of von Mises stress, and we can find a mean stress, an alternating, a mean stress, fatigue mean stress, in terms of von Mises stress. Now, what's important to note is not only in this von Mises term for stress amplitude and mean stress do we have the nominal stress, but if we have the presence of a notch, we also include the stress concentration factor due to the loading condition of bending, of axial loading, or of torsional loading. So we'll need to go and search for our SCF charts for each of these types of loading, calculate their values, and put them into this combined fatigue von Mises stress set of equations. Now, a couple things to consider in these equations is that because we are combining multiple types of loading, when we go and find our endurance limit, we should set the load factor equal to 1. We should not try to apply load factors for each one of these scenarios. We're just going to assume an initial load value of 1 and assume that the von Mises equation itself, is correcting for the differences in the different loads. Another important thing to note is that we should select the lowest size factor, KB, predicted for our shaft. And that's because, our shaft can have different diameters along it as it transitions from large to small diameters and such. So we should select the smallest size factor, which gives us a conservative design for the entire shaft. And then finally, a rotating shaft leads to completely reversed bending stresses, even if the bending stress applied to the body is static. So if we have a bending moment that's applied to our body and it is rotating, well, that bending moment creates stresses that are fully reversed, going in equal parts tension and compression. Now, how do we think about this? Well, let's assume we have a cylinder. it's subjected to a constant bending moment. If it was not rotating for this state of moment, the bottom would be in tension, the top would be in compression. However, if we load it with this bending moment and it is a rotating shaft, then as the shaft rotates, each part of the surface is going to go through equal parts of max tension and max compression, pulsating through zero across the neutral axes. And so this is where, even if the mean stress is constant, if it's a constant load, if the shaft is spinning, it'll go through equal parts tension and compression. And now our final aspect of this combined loading is, how do we check for yielding under this condition? Well, our yield check is going to be the safety factor of yielding is equal to the endurance limit of our material divided by the von Mises stress, where here the von Mises stress is evaluated against the maximum normal and maximum shear stress of our fatigue cycle. So this is, just taking the max value from our fatigue stresses and plugging it in to see if in these opening modes, in these tensile type of modes, will yielding occur. Now, if the max normal and shear isn't readily available to us, but we have the amplitudes and the means, we can use a conservative alternative that the yielding safety factor is equal to the endurance limit divided by the stress amplitude in von Mises plus the mean stress in terms of von Mises. With this said, we have the tools that we need to solve fatigue problems that have multiple types of combined loading.